All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 14.3, which deals with the ideal gas law. Now before we get into the details of these notes, there's a few objectives I have for you that you should be able to accomplish by the end of this video. So objective number 1, relate the amount of gas present to its pressure, temperature, and volume by using the ideal gas law. And objective number 2, compare the properties of real and ideal gases. So we start out here with the ideal gas law. And the ideal gas law describes the physical behavior of an ideal gas in terms of the pressure, volume, temperature, and number of moles of gas. Now, just like the other gas laws that we've seen, the ideal gas law also has a formula associated with it. And the formula for the ideal gas law is P times V equals N R T. Now let's go over what each of these variables are and what unit they need to be in. So our P stands for pressure, and it needs to be in units of atmospheres or ATMs. The V stands for volume, and it needs to be in units of liters. The N stands for number of moles of gas, and it is in the units of moles. And then our R stands for the ideal gas law constant, and that value is going to be 0.0821 liter atmosphere per mole Kelvin. And the T stands for temperature, which it needs to be in the units of Kelvin. Now, the difference between this formula and our other gas laws formulas is that we introduced two new variables. The first new variable is the N for the number of moles of gas, and then we also introduced this R, which is the ideal gas law constant. Now, the reason that we have to have these specifics these specific units for P, V, N, and T is because our units for our ideal gas law constant are these specific units, okay? So know that we have to convert these things to these units, and that our constant is always a given, and because we have these given units, we have to have everything else in those units. All right, so now let's take a look how exactly we get to the ideal gas law. How exactly did we get to this formula? So we start this off by talking about the combined gas law, which if you remember from the last section is P1 times V1 over T1 equals P2 times V2 all divided by T2, okay? And we ask ourselves this, or we make this statement. For a specific sample of gas, the relationship of pressure, volume, and temperature is always the same. So in other words here, with this statement, we could say this, that we could have our pressure times our volume divided by our temperature equal a K, and that K right there, that K is considered a constant. Now, this K is a constant because the amount of gas present, the K is a constant based on the amount of gas present. And we call that number or amount of gas present in for moles. And so we can go now one step further with this. We know now from this statement here that K could equal in R. And we get this definition of K equals N for number of moles times R, which we'll talk about here in a second, from experiments on using the variables P, T, V, and N. Okay, so if we put all of this information together, what we're going to do now is we're going to substitute our N times R for K. So if we substitute N times R for K, what we would end up doing is this. We would get PV over T equals N times R. And if I rearrange that by cross multiplying NR times T, what we would end up with is this. We would get PV equals nRT, and this R is that ideal gas law constant. And that R came from those experiments where they use P, T, V, and N to determine what the value of R is. Now, just as a reminder, the value of R is 0.0821 liter atmospheres per mole Kelvin. And this is experimentally finding or using those values of P, T, V, and N. Okay, so remember this is a very important formula as we go through this process. Now what we're going to do here is we're going to go over the steps of how to solve a problem utilizing the ideal gas law. Okay, so the steps to solve the problems with the ideal gas law is as follows. Number one, you need to write down the formula for the ideal gas law, which remember is PV equals nRT. Once you have the formula written down, you need to write out your knowns and your unknowns. And so just as a reminder, the P is for pressure, and it needs to be in units of atmospheres or ATMs. The V is for volume, and it needs to be in units of liters. The N is for the number of moles of gas. And the R is the ideal gas law constant. And remember, it needs to be in units or in a value of 0.0821 liter atmosphere per mole Kelvin. And then the T is for temperature, and that needs to be in the temperature scale of Kelvin. Okay, so once you've listed out your knowns and your unknowns, if necessary, you need to make your conversions. And so more oftentimes than not, you'll have to convert pressure. So what I provided is the equivalent to 1 atmosphere, and you can see all of these different units of pressure just in case you run into that scenario. Now, most likely you'll also have to convert your volume and temperature. We've done that before, but you may want to look back on your SI prefixes and how to go from one unit to another. Now, the other thing you may have to convert is moles of gas. Sometimes I'll give you grams of a particular gas, and you'll need to convert it using its molar mass to moles of a gas. Now, once you have all conversions into the correct units here, you're going to place the values back into the formula and solve mathematically. Okay, so let's go ahead and go through one of these problems and see if we can solve using the ideal gas law. Okay, so our example problem here says calculate the number of moles of gas contained in a 3-liter vessel at 300 Kelvin with a pressure of 1.50 atmospheres. So again, we're using the ideal gas law. So the ideal gas law formula is PV equals nRT. Okay, now what we need to do is list out all of these variables here. So we have our pressure, and if we look here, our pressure is in the units of 1.50 atmospheres. Our volume is a 3-liter container here for this gas. And then our N. N stands for number of moles of gas, and that's what this problem is trying to find. So our N is actually going to be our question mark. Now the R is a constant. So the constant is always, in this case, 0.0821 liter atmosphere per mole Kelvin. And then our T for temperature is in Kelvin, and it's 300 Kelvin. So we put that in here. Okay, so now what we have is this. We have all the players of the game, but we have to double check our units. Remember, it's always important to have the correct units for our ideal gas law. So pressure units should be in atmospheres, ATMs, which it is, that's good. Volume units should be in liters, and our unit is liters, so that's good. And then our R, remember, is always going to be liter atmosphere per mole Kelvin. And our temperature is 300 Kelvin, and it needs to be in Kelvin. So we're actually good to go on our units. We don't have to do any conversions at this particular problem. So we can go ahead and put these numbers back into the equation and solve via mathematics. So we'll have 1.5 ATM times 3.0 liters equals our N, which we don't know, times our ideal gas law constant, times our temperature, which is 300 Kelvin. Okay, so now we need to get N by itself. So because 0.0821 and 300 are attached via multiplication, what we need to do is divide each of those things on each side. So we're going to put a set of parentheses, 0.0821 liter atmosphere per mole Kelvin times our 300 Kelvin temperature, and what we did to one side we're going to do to the other. So again, we're going to have 0.0821 liter atmosphere per mole Kelvin times 300 Kelvin. Okay, so what I'm going to put in the calculator is this. I'm going to put a set of parentheses, 1.5 times 3, close that set of parentheses, and then divide it by another new set of parentheses, 0.0821 times 300. All right, so here we go. All right, so parentheses, 1.50 times 3.0, close the parentheses, divide it by, new set of parentheses, 0.0821 times our temperature in Kelvin is 300, close that parentheses, and we get a value of 0.183. Okay, so our N is 0.183, and if you've already memorized the units, that's great, but just to show you what happens here is our units with atmospheres would cancel on top and bottom, our units for liters would cancel on top and bottom, and then our Kelvin, because it's in the bottom portion of our ideal gas law constant, it would cancel out. And the way that this is set up, you basically have the number over 1 over mole, which means that unit would be moles. Now, like I said, sometimes it's easiest just to memorize what the unit is, so that way you become familiar. The key takeaway here is that we have to have the correct units because of our ideal gas law constant. So we have to have units that are seen like this, or else the problem will not work. Okay, so now let's go one step further. We're going to kind of tie a few things we've done before in science to what we're doing right now. And so it says density in the ideal gas law. And then it ties this in our question. It says, hey, what is the molar mass of a pure gas with a density of 1.40 grams per liter at STP? Okay, so we threw two things at you. One, density, and molar mass. And we've seen these things in physical science before, and in chemistry, we've used those as well. But now we have to think, okay, it uses the ideal gas law, but how can I use it? So what I'm going to do is I'm going to show you how we go from the ideal gas law and incorporate the molar mass and the density. So we start out here with PV equals nRT, the ideal gas law formula. And then I'm going to start over here. I'm just going to write this down. Density is equal to mass divided by volume. All right, so I'm going to do a couple of things. I'm going to multiply each of these areas by our mass divided by volume. And I'm also going to substitute in for the actual unit of moles. So I'm going to put this down here. N is equal to moles. And so when we do this, we're going to have this. We're going to have P times V equals moles times our RT. Okay? Now, I'm going to multiply each side by our density, which is mass times volume. So again, I'm just going to say mass divided by volume, mass divided by volume. I essentially added this or tacked this in, similar to how we would do this with algebra. Well, look here. We have volume and volume. So what can happen here is this. We can actually cancel out our volume, and we can rewrite this as such. So we have M times P equals mole times RT times M over V. Well, let me do this. I want to get rid of this mole, and this is going to be really important. So I'm going to divide each side by mole, and I want to take a look at this term. M is for mass divided by mole. And so I'm going to write that down here. M divided by mole equals mass divided by mole. Well, what is the definition, or you think to yourself, what is the definition of molar mass? Well, the units, if we think about that, the units for molar mass is grams divided by moles. Well, okay, if we have mass in grams, let's say we do, because that's the mass you would use for density, and we had grams over moles, this is equivalent to our molar mass. And we call this, or we show our molar mass with a fancy M. So this symbol right here can be kind of one of these fancy M's to represent molar mass. That's the symbol that we use. So I'm going to do a couple of things here. We're doing a lot here. I'm going to cancel out my moles because they cancel out on my right-hand side. And then M over mole. I just got done saying that that is equivalent to molar mass. So now what I'm going to write this as is our molar mass, that's the M, the fancy M, times our P for pressure equals RT times MV. Now, I want to do one step further, and that's because we use density. Instead of M divided by V, I'm going to substitute that for D for density. Okay? So what I'll do here is, again, I'm going to replace M over V. I'm going to replace M over V with D for density. So we have the M for molar mass times our P for pressure equals RT times D for density. Now I'm going to do one more thing because I want to isolate molar mass by itself. So I'm going to divide each side by P. I'm going to divide each side by P. And then I'm going to rearrange this. I'm going to put the D out in front. Okay. So our fancy M, molar mass, is equal to DRT over P. Now, I'm going to circle this formula because it's really important, but I want to discuss the variables, and then we'll finally get to doing the particular problem. So the fancy M is the molar mass of the gas. The D is the density there. And then our ideal gas law constant is still the same ideal gas law constant, and that is R is equal to 0.0821 liter atmosphere per mole Kelvin. And we get to our T for temperature, which, again, it needs to have specific units. It needs to have specific units of Kelvin. So let's make sure we have that correct. And then our P for pressure needs to be in atmosphere. Okay, so I know I've taken a lot of room. I'm going to grab another sheet of paper so we can actually do the problem that is shown up above. Okay, so I am going to box this in here, and I don't need you to know how we went from PV equals nRT to molar mass equals dRT over P. What I need you to do is I need you to be able to apply this particular formula. And this formula is given to you. And I just want you to know that we can manipulate our ideal gas law formula to get to this particular point. Okay, so I'm going to leave that right there. And I know we don't have the problem in sight here, but I can read that to you as we go through this problem. So the problem itself says, what is the molar mass of a pure gas that has a density of 1.40 grams per liter at STP? So we're going to use the molar mass of a gas formula, which is M equals dRT over P. So our molar mass, that is the question that the problem is asking, and so that's our question mark. And our D for density, if we read our problem, the density is 1.40 grams per liter. The R is still the same ideal gas law constant, so it's 0.0821 liter atmosphere per mole Kelvin. Okay, and then our T and our P, we have to do a little bit of work to find this. So if you think back to section 2, remember STP stands for standard temperature and pressure. And so STP, the temperature, is 0.0 degrees Celsius. But again, we need it in Kelvin. So what we have to do is we have to add 273.15 to that number, which is pretty easy. 0 plus 273.15 is 273.15 K for Kelvin. And then our pressure for standard pressure, if you read that problem above, is 1 atmosphere. So pressure is 1 atmosphere. Okay, so now we're going to put this all together and we're going to solve for the molar mass of this gas. So we have our M equal our density, which is 1.40 grams per liter, times our ideal gas law constant, 0.0821 latum molk. And we multiply that by our temperature, which we just found to be 273.15 K for Kelvin. And we divide all of that business by the pressure, of 1 atmosphere. All right, so we're going to put this all in our calculator. Again, what I suggest, if you have to multiply or divide many things on top or bottom, you put it in a set of parentheses. So what we're going to do here is we're going to take 1.40 times 0.0821 times 273.15, divide that by 1.0, and we get a value here. I'm going to use 3 total digits of 31.4. Okay, so our molar mass here is 31.4. Now, some of you may recognize, hey, I have molar mass, so I know the unit. But I'm going to show you how to get to the unit via how we can solve this. So we start out here with our units of liters. It's on top and it's on bottom here. They cancel out. Atmospheres is on top here and on bottom. They would cancel out. Our temperature unit, K for Kelvin, would cancel out. And so we're left with gram per mole. So our molar mass of this gas in this problem is 31.4 grams per mole. All right, so now we're going to talk about one more topic that we've talked about so far, but we really haven't gotten much detail. Okay, so that topic that we are talking about here is one that distinguishes ideal from real gases. We've talked about ideal gases, and we say kinetic molecular theory assumes this and that, and we consider these gases to be ideal. But what really is considered an ideal gas? Well, an ideal gas is going to occupy a negligible volume, and also these ideal gases are far enough apart to exert minimal attractive or repulsive forces on each other. And so with an ideal gas, to go a little bit further on this point here, we're going to assume that gases do not have intermolecular forces. And so if we put all of that together here with an ideal gas, they're going to follow the gas laws under all conditions of temperature and pressure. Now, if we take all of these things into consideration, where something doesn't have an intermolecular forces, or they're actually going to follow those gas laws to the T under the conditions of temperature and pressure, they have this, or we can say this: no gas in the real world is actually ideal. Now, if no gases are truly ideal, well, what makes a real gas different from an ideal gas? Well, in a real gas here, what actually happens here is that it's going to have some volume. Now, in a real gas, the volume itself is pretty small for a couple of reasons. One, the size of atoms are small. Number two, the lengths of bonds between atoms are also small. And no matter what gas we actually have in the real world, those particles are going to be subject to intermolecular forces. So a real gas is only going to behave like an ideal gas under certain conditions of temperature and pressure. Now, when we have the right temperatures and pressures, the ideal gas law is going to give a close approximation of how real gases act in the real world or through experiments. Now, real gases deviate from ideal gas behavior under the following conditions. One, there's extremely high pressures. Two, there's extremely low temperatures. And so what happens here under these conditions, why a real gas deviates from ideal gas behavior, is that the particles and speed of the gases are going to number one, have less space, and the speed is going to move faster as well. And excuse me, that's the speed and space, they both decrease. And so what that is going to do is it's going to affect the volume and the intermolecular attractive forces between the gases. All right, so that concludes this section of notes. We took a real deep dive in the ideal gas law and its formula. It has some really important things that we need to discuss later too, so it's not something that we just do this section and are done with it. And again, we have learned a lot. I hope you've enjoyed this episode, and as always, if you haven't done so already, make sure you subscribe.